So the problem that we are going to discuss today was yeah. So we'll discuss knapsack for all subsets today. So if you are given a sequence of so the problem is that you are given a sequence of n positive integers a1, a2, an and another positive integer s. So for a non-empty subset T of the set 1 to n, so your original set here of 1 to n is here the indices and not the actual elements. So a non-empty subset T of the original set, let us define a function over that, and the function f of t is the number of different non-empty subsets x1.
Excuse me, ma'am.
Yeah.
Sorry to interrupt, but can you, if you will, you be sharing the screen because the screen is not visible yet.
Oh, it's not.
Yeah. Yeah, it's visible now.
Okay. Okay. So we are solving this problem today, knapsack for all subsets. Here you are given a sequence of n positive integers a1, a2, an and another positive integer capital S. So for a non-empty subset T of the set original set of integers a1 to an, let us define f of t as f of t is the number of different non-empty subsets x1 x2 sk, let's say this is 1 of t, such that the sum of these numbers ax1 plus ax2 axk is equal to s. So you are given next you need to find the sum of ft over all 2 to power n minus 1 subsets t of 1 to n. Since the sum can be enormous, printed modulo this big value. All the values in the input are integers, and actually positive integers, one more than 1, less than equal to 3000, and the input format is that you are given first two positive integers n and s. N is the total number of elements you will get, s is some other positive integer, and next line will be n positive integers, and you have to compute this function f of t. Okay, now I will just go to the whiteboard to explain the problem once again. So we have n numbers and some value s, and then how many how many non-empty positive subsets are possible of n elements.
And those would be 2 raised to n minus 1.
Yeah. So we have 2 to power n minus 1 possible subsets, non-empty subsets, which is t here in the question. So they have defined this as t in the question here. So for now, for each such non-empty subset P, you will again find subsets, non-empty subsets of T, and for every non-empty subset, for every non-empty subset of T, I just forget to change my screen. For every non-empty subset of T, we are going to compute this function. Like, let us call this non-empty subset, in the question they've called it x1 x2 dot dot xk. Let's say one subset is this. Then we compute the sum of all of these numbers, which is ax1 plus ax2 plus dot dot axk. And if this is equal to s, then we increment our count. So we compute this value, and if this value is equal to s, then we increment our answer. Because answer is the total number of such non-empty subsets which the sum of which is equal to s. So this is f of t. This value is f of t, and now you have to compute the sum of f of t. Is the problem statement clear?
Yes, ma'am.
Okay.
So the approach, can I share that I'm thinking right now after looking at this?
Yeah.
So what I think is, first of all, let us do a brute force recursive implementation of this. So we'll create a recursive function rec which will have two parameters. The first parameter would be a position, let's say which index that we are at, and the second parameter would be the sum, the remaining sum that we can achieve or we have to achieve, right? So it will have a position and a sum. Now, if the sum is less than 0, then we'll return 0, because we can't have any subset that have like a sum exactly equal to s.
If remaining sum is equal to 0,
Is less than 0,
oh, less than 0, yeah,
then we'll return 0.
okay, okay.
We return 0 here. Otherwise, if
Yeah.
Otherwise, if the sum is exactly equal to 0, I mean the remaining sum is exactly equal to 0, then we return 1, because we can have this as a subset.
Yeah.
Or otherwise, in the last case, what we'll do is we'll check if we can, if the sum is, there is remaining sum of greater than 0, then we'll still have to add some numbers. So what we'll do is we'll recursive call it for two cases. One is if we take that element at the position, or one is if we don't take the element at the position, and then we'll add them up and return them. Also, what I just noticed is in the case if the sum is equal to 0, along with 1, we'll also have to return like the value if we don't take that element right away. So that would be 1 plus something, 1 plus recursive call of position minus 1 remaining sum. And if position is less than 0, then we'll return 0, I would say, because we don't have any remaining elements. So we can keep that as an or condition in the first condition only, remaining sum is less than 0 or
Okay, but what did you say in the second else if s equal to 0 and position is not 0?
Yeah, if s equals to 0, then what we can do is, if position is not 0, then we can return 1 plus recursive call of position minus 1 comma remaining sum.
But you said no, remaining sum is equal to 0.
Uh, yeah, remaining sum is 0. Okay, okay, yeah, we'll have to return 1. Okay, yeah, right. If sum is equal to 0, then we'll return 1. Sorry, return 1. That is okay. And yeah, so in the else condition, we'll do just 2 recursive calls, one with taking the element as position, one without taking the element as position.
Okay, so you are saying two rec calls, one is taking position, there will be something here, one is not taking it.
That is position minus 1 because we are not taking it.
Yeah, and then what is
We return the sum of these because we have to consider both the conditions.
okay.
Also, in the first condition, we'll also have to add another base condition that if position is less than 0, then also we return 0 because otherwise it will go just in a recursive level.
That should handle it.
Yeah, and if this recursive approach is working, then we can also memoize it later on to make it go of n into s.
Hmm. Hmm. Okay. Yeah, the idea is correct, that we will consider whether we are at position and we'll consider whether to take this and not or don't take this. Yeah, and then accordingly our remaining sum will update here if we take the element if we don't take the element or take the element. So I think in both of will it be position only?
Yes, ma'am, I think it will be position only because we are checking the element on the basis of position and the remaining subset. All the subsets will be considered, either we take it or not take it.
Yeah, but if we keep calling, so we enter the function from position and we are calling
position and the second value will be sum minus the value at that position because we are taking it, right? So yes, sum will be reduced for that.
Yeah, sum will be reduced, but this value, this should also become position minus 1.
Yes, ma'am, this should also be position minus 1, right? I actually got it, like unbound.
Yeah, so this now is showing that we took that element and our remaining sum is less. So we got that. Here we don't take that element and our remaining sum is not.
Also, one thing I would point out is that the way in which we have written condition, I think we should write sum equal to 0 return 1 before this first condition, so that if we have got a negative index but the sum we have achieved is 0, that means after taking the last element our remaining sum is 0, then we will also return 1 for it, right? So I think the order of our conditions should be like reversed for first condition.
Or we can start our element indexes from 1. That is.
Yeah, maybe.
Yeah, like in the question, I think it was given from 1. So assuming from that, yeah, otherwise we'll have to take care of these conditions, corner cases. Right? Now, okay, fine. Now we have seen this approach. Now let us take the example that is given in the question and try to run it through this one. Yeah?
Sure.
And then we will see how it works. So then So first example is 3, 4, 2, 2, 4. That means there are 3 elements. S value is given as 4 and the first element is 2, second is 2, last is 4. Okay. Now in the we have been given a solution for this problem. So let us try this solution. So let us find. So what is in the question? The question says that first you have to go over every possible thing. And what is every possible thing here? So yeah, every possible thing here is first element, second element, third element, first and second, first and third, second and third, and all the rest. These are all the possible non-empty subsets of the original set. Okay. Now, what is f of t? So f of t actually goes over all of the non-empty subsets of t. So what are the non-empty subsets of t? So here we write subsets of t. In the first case it is only 1, second it is 2, third it is 3, fourth it is 1, 2, 1, 3, and the last one. What will be the subsets of the last one?
I noted something somewhere wrong because I tried to consider with the problem is like the number of subsets having the sum equal to s. I think I got this somewhere wrong.
Yeah, that's alright. Here I yeah there's like few guidelines are required, but we will you can figure it out I think with the help of an example. So we'll just run through this example and see. Yeah. So we have listed all the possible t. Now we have also listed all the possible subsets of each t. Now for the last t, which is 1, 2, 3, what are the non-empty subsets of this?
That would be all the subsets that we have considered already 1, 2, 3, 1, 2, 2, 3 and 1.
Yeah, so it is all t.
Yeah.
So you can see here that we are doing redundant work here. So we would for example compute that whether 1 comma 2 actually satisfy that condition or not. Ax1 plus like a1 plus a2 is equal to s or not. We will check it here also and we'll require it here also. And similar is the case for others. So subsets are being repeated and we are going to do this repeated work which we want to optimize here. Or like initially let's not consider about the optimization part, so we are just going to let's see how to complete that. So let us now what is next part? The next part is compute f of t is how many subsets of t have sum equal to x. Here x value is given as 4 and a1 is equal to 2, a2 is equal to 2 and a3 is equal to 2. has only one subset, one element, that is the first element as a subset. What is f of t?
That would be because no subsets are up to 4.
Yeah, and for the second one?
For the second one as well and the third one as well.
Second one, a2 is equal to 2 and is not equal to s. For the third one?
That would also be 0.
No, check again.
I think for the 3 we have only like 3 as a subset.
Yeah.
So that would be 0 because it is not equal to 4, right?
No.
Because they are given as equal to 4.
No, a1 is equal to 2, a2 is equal to 2, a3 is equal to 4.
That is
Yeah, they are given a3 is equal to 4.
yeah. In that case that will be 1 because this value in this subset would be 4. So the sum would be
Yeah, so here we have 1. Now for 1 comma 2, then t equal to 1 comma 2.
yeah, then also the value will be 1 because the first and second subset will be 0 and from 1 comma 2 would be 4.
Yeah. For the third one, for the 1 comma 3,
That would also be 1 and for 2 comma 3 it would be 1 as well.
yeah, and for the last one,
For the last so that would be 2.
yeah, and what will be the answer?
That would sum up to 6.
Yeah, right. So here we what do we see? So like in the last one we had used the previously computed values and there was only this new one subset here, but so the example run is clear, right? Now it's not good enough. Yeah, so then now as we were discussing earlier that if we are at some position say I, and then how do we approach? So let us do that now. So what will we do? That let us consider we have these elements 2, 2, 4 and let us say that we have computed f of t till the first 2 and we were, so I is equal to I is at 4 and we are trying to compute the answer for the, sorry, I is not 4, so I is equal to 3 and we are trying to compute it for I equal to 3 using the all previously computed answers for I is equal to 2, I is equal to 1, I is equal to 2 actually. So then we have only 3 subsets possible with first 2 elements 1, 2, 3. For this one answer was 0, for this one 0, this one it was 1. Now we have f of 3 comma 4. That's what we are trying to conclude here. See that we are starting from the last index, okay, and we have all of the sum remaining right now. So we have s is equal to 4 and we are the last, so we are trying to compute this. So then first would be when we take the third element, so it will be f of 2 comma 0 plus f of 2 comma 4. that's what we had written earlier. So now what we have as an answer here is f of, here we have f of 2 comma 4 is equal to 1, isn't it? Like if we have these two elements and sum is 4, so this answer was 1, sum of these two. So if we place 1 here and then f of 2 comma 0, we have taken the last element and now 2 comma 0. So let us consider that now the sum is equal to 0. So we had kept the base case as sum equal to 0, remaining sum equal to 0 means we return 1. So we again return 1 here and our answer will be 2 then. But the actual answer is not 2, it's 6. So what have we missed here? We have missed some cases here.
Those would be the cases I think where in which we are having the subsets of 3, like 1 comma 3, 2 comma 3, 1 comma 2 comma 3, those subsets.
Yeah, so those subsets were there, but those subsets would be handled by this also. Yeah, but those subsets will be handled by this, no?
Yeah.
No, what we didn't do here, I think if we go back to that here, what did we not do? So here in our table we'll say we have counted 3, 1, 2, 3, 4 times. We are counting that subset 3 gives sum equal to 4 times, but in our equation we are counting it only once.
Yes.
Yeah, so that is happening because this is part of multiple subsets, these t, and in every t we again take the subsets and compute, so that is why it's happening. Similarly again for 1 comma 2, so 1 comma 2 also we are keeping like twice, not once. So that's why we are getting only 2, because currently we have considered only these distinct answers and not those, so we have to fix that. Now how do we do that? Let's give it a thought, 1 minute or so.
Can we go back down to the equations that we were making?
Yeah.
Okay, so the first one would give us a result of 1. The second one would give us a result of 1 as well.
Yeah.
Now the second one is giving the result which it is tasked to do. So this is okay. But in the first one, I think we should kind of multiply it with a constant. And for if not constant, we should just multiply the current value by 2, maybe, because we are considering those values all over again.
Yeah.
So the answer that we have yet multiplied by 2, something like that, not sure.
Yeah, but still will be less than 6. No, it's fine. So we look back again to this, what's happening here. Some computations are happening like, so you have to do twice, as you're saying twice, but the twice is happening for what? Which term were you saying twice for? f2 comma 0 or f2 comma 4?
That would be 1 comma 2.
Yeah. Here
Yeah.
that's.
So I also saw what I was missing here. So in all the previous iterations that we have done, like all the sub calls that we have already done, like 1, 2 and 1 comma 2. we'll also have to consider the current element if that sums up to the total target with the
Right.
remaining.
Right. Right.
So if the current one is equal to the total target, then we also add that as well, multiply by, I mean, for one for that and multiply by the number of subcalls that we have made already. So that would be like 3 plus 1 for the current this call. So 3 plus something that would be.
Mm.
So like if we were on position 3 and we have the answers till 2, then we'll do 2 raised to 2, yeah. So that would be 4. So we add 4 in, that would be the way.
Yeah.
If the current values sum up to the equal, is equal to, exactly equal to the remaining sum, then we'll do it. I
Right.
think that would be the way.
Yeah. Right. Because this value is going to get like when the sum is equal to 0, this value is going to get that many, what you are saying, 2 to power 2, as we can see in the example also, like 3 as a singular subset is occurring 4 times, once here, then again in 1 comma 3, 1 2 comma 3, and in the final 1 2 3.
Yeah, that is exactly what I was saying.
Yeah.
It will become an isolated set, and so it will have to be counted again and again for all
Yeah.
those previous recursions.
Yeah. Yeah, that will be 2 to power I minus 1. Now, so that will be the case where when we have this. So here we are going to change it to, as you suggested. So let's do that. So here we are going to change this one to 2 to power 2. Now, what about this one? Then other one. Why is it, so currently we have kept it 1, but it should be 2, and why is that?
Because all these values will occur as a subset later on somewhere in our example, right? As we talked about 1 comma 2, it will come back as 1 comma 2 later in 1 comma 2 comma 3.
Yeah, so all
So
of,
that
right,
all those would be twice.
right. So all of those subsets of I minus 1 elements, I minus 1 elements, I mean basically in our example 1 2 1 comma 2, they are getting repeated again in 1 2 3, and so whatever answer was there we had for singleton 1 singleton 1, so 2, and 1 comma 2, we have to multiply that answer by 2.
Yes.
And we have already considered the case for the this element. So okay, we'll multiply it by 2 here. So that will give us the answer as 6 here. So what happens when the sum, so in the first case here we have, so one of our call is happening at f I comma 1 comma s itself, the original sum. We have not decremented it, we have not chosen third element. The other one is happening when we have chosen it and we reduce it and we have some remaining sum. In that case, why will it be handled properly? Will it be handled properly? I mean, is this fine? Whatever we have written so far?
I think so we can just go back on the one start to the table that we are doing.
Yeah.
Here, one thing that I'm seeing is that in the case of 1, 2 and 1, 2, so the ones that are repeating again in the subsequent calls of 1, 2, 1, 3 and like so on, that would already be handled by, I mean, all those subsets which doesn't have 3 at all,
Yeah.
right? So for those like 1, 2, 1,
Yeah.
2 again in 1, 1 comma 2 and then 1 in 1 comma 3 and then 2 in 2 comma 3, these will be handled by the recursive function when we have called this for 1 comma 2, right? And for when we have called for 3, then we are already doing the task of like checking for the remaining, and I would say multiplying it by the 2 raised to power n, or the 2 raised to the remaining number of subsets. So the remaining length of the subset. Yeah. So I think this should just work fine.
Yeah, that is only in the case when it is equal to 0.
Yeah.
I mean that 2 to power I minus 1 is only in the case when sum is equal to 0. Otherwise, it is that value that we get by doing f of I minus 1 comma remaining sum. So we will get some value with that. Otherwise, it will be that value.
Yes, exactly.
And that value will be computed using the same recursion this recursion relation that we have written, and that value will be correct. So yeah, so this is, then let's write this finally in the form of a pseudocode. What we have is, we are going to call, let's say, recursion rec of I comma s. So if s is equal to 0, then you will return 2 to power I minus 1. Else we will return
I think we should make it just 2 to power I, because like when we have called the function and the sum has went to 0, then the I also went to minus 1, right? Already.
let us assume that where element indexes are starting from 1.
Yeah.
Yeah. So in considering that, this will be this. Otherwise, if you consider it from that starting from 0, then yeah, 2 to power I will do. So then this will be rec of I minus 1 comma s minus weight of I plus I minus 1 comma s. I think that should come after this then.
Yeah, after the S.
Yeah. Here we have to ensure that this is not negative. So we can put a if condition before doing this. That is required actually.
I think, yeah, I think we can do that with the position statement only, that if the sum is also less than 0, I mean as in our condition, if the sum is less than 0, then also we return 0.
Okay, okay. Yeah. Hmm. Yeah, I think this should work. And then we can memorize this. Yeah. So then we can memorize this. Currently the complexity is exponential because we are just going over every subset. And then when we memorize this, then what will be the complexity?
It would be 4 big O of n into S, because sum can go with the 1 down.
Hmm.
We have to consider all the possible pairs of I comma S, and that would be I mean 4 big O of n into S.
I mean, I think it's like exponential. Currently, it's around 2 to power n times 2 to power n. Order of this, like, which is it's order of 2n. Okay, 2 to power 2n, right?
Yeah.
Yeah. So currently the time complexity is exponential, and as you said, if we memorize it, it will become order of n into s. And we can memorize it by adding a statement here itself in this code that we already have. We can convert this recursive call itself to a memorized one by saving this value instead of like before returning the value. So here before returning the value we can save this value in a DP table, and whenever we are asked here to compute, we can check if dp of I comma s is not equal to, let's say, -1. If we keep -1 initialize it to, then we can just return that dp of I comma s. And we will have to initialize our dp table. Do we need to? No. So will this be sufficient?
I think this should be sufficient. And one more thing I wanted to ask is, like for creating the memo or the DP table, should we use array or like a hash map? Because I think hash map saves memory sometimes. Because all the calls are not going to be called right, all the possible ones.
Oh, hash map. Hash map is it also in C++?
Yes, ma'am. It is in C++ as well, like as an unordered map.
Okay.
Yeah, in Python then it is like a dictionary, and I think Java also offers it with the name hash map.
Hmm. So how will you do it in unordered map? So in that it is key value pairs.
Yeah, we can make pairs of like two values will be like their pair of two values will be the key, and the
Okay.
value that we get is the like the
Okay.
key of it. And if that key is not present in the hash map, then we consider it to be minus one.
Mm-hmm. Yeah, but searching time, searching for the key. So you'll find key, right? Do a find key operation there.
Yeah, finding the operation would be O of one only.
Yeah, in unordered map, I think asymptotically it is order of 1. Although in a real data structure it is usually, like if it is implemented even with binary search trees, it is log n, but unordered map give it as order of 1 asymptotically. So yeah, we can say that access time is probably similar, but array is definitely faster, probably. Like here we do not have an asymptotic guarantee. We know that it is order 1 access time.
Yeah.
So
this is like a space-time trade-off for both of the cases.
yeah, then it will be a space time. Usually, but in competitive programming, they give you enough space. So space is usually not a problem. Only time is the concern. Like usually, I think they give around 1 GB memory for each program to run. So memory is usually not a concern, and I have never tried using an ordered map in place of a DP table, but yeah, it could be you can definitely try this. And yeah, asymptotic guarantee is fine, but still, what about adding, inserting? How long does insert take?
So that also is open. I'm just thinking like, will it be like in the most cases, can we consider that the like map will store less data, because I don't think in the most cases all the recursive calls will be made, like all the possible pairs, right? So that way the memory will be saved much, and both will be nearly above one for every case.
Yeah, I mean, yeah, if it depends on the case, then the example, I mean, it depends on the input, that how many recursive calls will be made, and most likely not all of them will be made. So yeah, it can save space, but asymptotic guarantee, I think, means that when you do n operations, then every operation is taking around order of 1 time. But if you're doing only few operations, then is it still order of 1 time?
I actually was thinking about the case when the sum that we are given to begin with can be like much greater than, like there is, as I remember, it was 3,000, right?
Yeah.
Like if the sum is greater than 3,000, then I was thinking if this converter will work with the most of the average speed. So that is what I was thinking. And that if we use our table, then it will consume a lot of memory.
Yeah.
That's what I was thinking. Like if we should use like hash maps instead of like an array, then can it like solve most of the average cases for like yes.
So, but how much is the space even with that? So it is 9 into 10 to power 6 times 4. 36 10 into 10 to power 6 bytes, which is 36 megabyte. and usually in the platforms they give I think on the platforms like CodeChef and Hackering, I think they give much more memory than that.
Yes, I think we'll try both.
Yeah, like if some program, if the constraints are too high and then if the constraints are too large, then probably that those options can be tried. But what I'm saying is that in most of the cases you may not require to use a hash map instead of a DT table.
Yeah.
Although using an unordered hash map has its own advantage of, as you pointed out. Yeah, good point. I have never tried, so I cannot, like, I don't know how much advantage it will have in terms of time and workspace, like practically in problems. Okay, so the problem, so yeah, we've done this problem. It was a nice problem, and we have covered actually similar problems from this 01 knapsack and weighted scheduling, and even this one. All of them were similar problems in GT. Yeah. So I hope that solving these problem was helpful and could help you. It will help you like approach new problems. So yeah, I had only this much for today. Do you have any other doubt?